Every country aiming for the top is hungrily aiming at the US. China, Russia, North Korea. None is left out. But the US has something they all don't: an advanced sixth-generation fighter the world has never seen. This $300+ million fighter would end any war targeted at the US before the war even has a chance to begin. Packed with an avionics suite that makes it spot targets on the other side of the planet, an armament suite that enables it to strike targets on the other side of the planet, and a stealth suite that enables it to hide in plain sight. This new fighter is an aerospace revolution the world is probably not prepared for. Aerospace Revolution. Next Generation Air Dominance, or NGAD for short, is the program that'll develop the fighter that ensures the next generation of American air dominance, as the F-22 Raptor has done so excellently well for decades now. The new NGAD fighter will be slick and aerodynamic, and feature an elongated blended fuselage that completely shatters the laws of physics. Within this fuselage will be three war-defining technological wonders: an AESA radar, stealth, and adaptive cycle engines. AESA radar. The NGAD program is also developing new and advanced active electronically scanned array radars that would power the fighter's sense-all, kill-all advantage. Active electronically scanned arrays, or AESA radars, have many advantages over the previous generation of radars. They cancel out the need to mechanically scan rapidly in different directions. Therefore, they lack all the clunky moving parts of their predecessors, making them far more reliable, and in some instances, more compact and lighter. They can scan huge volumes of airspace and large areas of the planet's surface extremely fast, simultaneously keeping track of multiple targets with peak reliability. They complement these capabilities with high sensing resolutions, immunity from electronic warfare attacks, enhanced performance against stealthy targets, and being stealthy themselves. For even better performance, the NGAD fighter will do away with the traditional radar mount for the more futuristic electronically configured smart skins integrated into the aircraft's fuselage. This allows the AESA radar to offer a level of sensor fusion never seen before. By fusing the functions of the sensor, electronic warfare systems, and communication systems into single multi-mode AESA arrays instead of multiple systems each doing one thing, AESA radars alone now have it all. Super fast scanning, spherical coverage, very high power, electronic warfare data, identification friend or foe, precise narrow beam abilities, and wideband capabilities. The data from all the individual functions are combined to form a detailed, seamless, tactical, godlike picture of the battle space. Using such self-sufficient AESA radars would make the aircraft system easier to upgrade both in terms of software and hardware. Testing and validating the multiple functions could also be accelerated, at least drastically. Under the NGAD program, that would be particularly useful. NGAD is touted by the Air Force as a program that'll birth an entire family of systems, including the manned sixth-generation fighter, radars, unmanned fighters, and so on. Should the manned and
Research Service estimates that firing a high-powered laser will cost somewhere between $1 and $10, just a fraction of the $1 million to $10 million that defensive missiles cost. Using million-dollar missiles to fight off swarms of relatively cheap enemy drones, or cruise missiles, is what those analysts call a negative cost exchange ratio. In 2014, the Navy installed the first laser on a ship for sea trials. Fitted forward on the deck of the amphib transport ship, the USS Ponce, the 33-kilowatt ANSEC-3 laser weapon system, LAWS, has a short, round firing tube painted white. Two smaller tubes for sensors rest on the shoulders. To an untrained eye, it looked like an amateur astronomer's telescope, but even this early, low-power version delivered striking firepower. A second, stronger laser entered trials in 2019. Then, in August 2022, the Navy installed its first permanent laser on a destroyer. The Arleigh Burke class, Preble. Developed by Lockheed Martin, The weapon has a 60 kilowatt power output that integrates with the ship's advanced Aegis radar and weapons control system. The Navy calls it Helios, or high-energy laser with integrated optical dazzler and surveillance system. Later versions could be even more powerful. Lockheed Martin says the weapon could eventually scale to 150 kilowatts. But even at that strength, it will be most useful against drones and small surface ships. To stop a barrage of cruise missiles or a hypersonic weapon barreling toward the USS Ford at Mach 5 or faster, the Navy needs something much more powerful. To thwart cruise missiles, the Navy estimates that it needs at least a 300 kilowatt laser. In addition to the size and speed of those missiles, their nose cones are made out of such materials as pyrolytic graphite or pyroceram ceramics designed to withstand the high heat inherent to supersonic flight, which can top 1,000 degrees Fahrenheit.
This footage is 100 years old. It shows part of the military exercises that took place off the east coast of the United States between 1921 and 1923. The Martin MB-2 airplane is emitting a trail of chemical smoke that rains down to the surface of the ocean, forming a dense smoke curtain hundreds of feet tall. The smoke is created from a highly toxic chemical called titanium tetrachloride. It's a colorless liquid that reacts with air moisture to form the smoke you see here, which consists of hydrated titanium acid and hydrogen chloride. It is dangerous to work with, an irritant to respiratory systems, and can corrode metal. It's not hard to imagine how this process of delivering huge chemical payloads by airplanes at altitude would be important to later developments in geoengineering and cloud seeding. If they were doing this 100 years ago, imagine what they can do now.
Wow, the B-2 is the only stealth strategic bomber in the world that can't be replicated even if you give away the blueprints. First off, the B-2 is quite a unique aircraft because its entire body is basically one big wing. That's what gives it incredible lift. But here's the catch. How does it control its lateral movement when it doesn't have those vertical tail fins? How does it make turns? Well, it does something pretty cool. It manipulates the exhaust flow from its two engines, one fast, one slow. By doing that, it can turn towards the side with the slower exhaust flow. Plus, it's got up to 11 spoiler panels on each side of its triangular wing. To make a safe turn, you've got to precisely control the airflow around those engines and each spoiler panel. So even if the B-2 has as many as 10 pilots on board, they can't handle all this manually. It needs an incredibly complex flight control system to make it work. That's the secret sauce behind the B-2's ability to fly. Now, when it comes to writing the software for this kind of flight control technology, well, that's no small feat. And honestly, it's something only the US has mastered. Other countries might nail the aerodynamics of the shape, but it's the software that's the real challenge. And let's not forget about the high-end precision manufacturing needed. I mean, just look at the B-2. You can hardly spot a single rivet on its sleek surface because it's made with one-piece casting. Imagine that wingspan is over 52 meters. How do you maintain such high precision over that kind of distance in your machining? If you can't achieve that precision, you end up with all sorts of bumps and irregularities that mess with radar waves, and that's a no-no for stealth. So, even if the US shares the blueprints, it's still tough for other countries to replicate the B-2, mainly because of these reasons. Cool stuff, right?
Do you know how fast the world's fastest fighter jets really are? This is the Swedish Saab 35 Draken and the European Eurofighter Typhoon, both traveling at 1,534 miles per hour. That's the Russian Tupolev Tu-160 at 1,573 miles per hour. This is the American F-16 and the Russian MiG-21, both traveling at 1,573 miles per hour. This is the Swedish Saab 37 Viggen and the Russian Sukhoi Su-57, both traveling at 1,611 miles per hour. This is the Panavia Tornado ADV from the UK, Germany, and Italy, and the Mirage 2000 from France, both at 1,688 miles per hour. This is the American F-104 Starfighter, traveling at 1,688 miles per hour. This is the Russian Sukhoi Su-47 at 1,695 miles per hour. This is the American F-4 Phantom II at 1,711 miles per hour. Now we're looking at the Russian Sukhoi Su-35, the US F-22 Raptor, and the Russian Mikoyan MiG-35, all traveling at 1,726 miles per hour. This is the British English Electric Lightning, traveling at 1,764 miles per hour. This is the Russian MiG-29 Fulcrum, also at 1,764 miles per hour. This is a Russian Sukhoi Su-27 and a Russian MiG-23 Flogger, both traveling at 1,803 miles per hour. This is the US F-14 Tomcat, at 1,841 miles per hour. This is the US F-15 Eagle and the US F-111 Aardvark, both at 1,918 miles per hour. This is the Russian MiG-31 Foxhound at 2,171 miles per hour. This is the American XB-70 Valkyrie at 2,378 miles per hour. This is the US Bell X-2 and the Russian MiG-25 Foxbat, both traveling at 2,455 miles per hour. This is the American State Route 71 Blackbird at 2,547 miles per hour. This is the American X-15 at 5,140 miles per hour. This is a submarine invented by the United States more than 200 years ago. A man with a bomb rides a specially made boat under an enemy warship, ignites it and escapes. Before completing this procedure, the pilot was not allowed to surface in case he was spotted by the enemy, which prevented him from breathing fresh air. Engineers used the project to make a barrel-shaped shell and sealed the joints with rubber to prevent water from entering. The pilot only needs to fill the water tank through the valve to sink the submarine to a depth of 6 meters. There was a waterproof explosive on the back of the submarine, which he tied with rope to a drill. When the pilot reaches below the front battleship, he can attach the explosives to the bottom of the ship through a drill. However, the pilot tried various methods, but could not penetrate the hull, and with only 30 minutes of oxygen inside the submarine, he was forced to abandon the mission and return to the surface. The engineers replaced the drill with a harpoon, and enlarged the hull so that it could hold 9 men inside, with the pilot steering the hull through a lever at the bow to aim, and the remaining 8 sailors working together to crank the boat so that it could move quickly until it hit an enemy warship, thrust the harpoon into it, and then detonate the mine, sinking the target. Although the design made the submarine highly maneuverable, it still needed a collision mode to attack the target, which made it easy for the enemy to detect it. So the engineer put a can of compressed air into the torpedo. When the torpedo is fired, the compressed air valve inside opens and releases air to drive 2 pistons to power the torpedo, but the bubbles released by the compressed air can easily reveal the torpedo's track and allow the enemy to avoid the attack early. Engineers had to switch the weapon's power source to a small engine, which required a large battery to power it, resulting in the torpedo being more than 7 meters long. To carry enough torpedoes, submarines need to be bigger. Because submarines are so large, they quickly run out of fuel, so engineers built a special type of submarine to carry fuel, which can hold 400 tons of fuel inside. Whenever other submarines needed refueling, he would surface, and the crew would drag the fuel pipe to refuel the submarine. During this time, the 2 submarines were vulnerable to attack. So engineers fitted the submarine with a nuclear reactor, which used the energy released by uranium atoms to heat water to more than 250 degrees to produce steam. The steam was then piped into a turbine, which turned the turbine, turned a huge gearbox, and then drove the propeller, providing a constant stream of power for the submarine. Because the nuclear reactor was so large, the submarine had to be enlarged to more than 100 meters in size. With more space and more crew members, the submarine's interior began to run out of oxygen, so engineers installed an oxygen generator on the space station inside the submarine, which uses electricity to split water into oxygen and hydrogen. The machine can produce 4,000 liters of oxygen per hour, all of which are piped into each chamber. Today's submarines only need to carry some uranium to operate underwater for 20 years. With great power, the weapon also needs to be upgraded. So engineers replaced the torpedoes with 16 intercontinental missiles, all armed with nuclear warheads, with a range of 12,000 kilometers and 40 times the power of a Hiroshima bomb. And so the perfect submarine was built.